So I want to thank Alex and Ham for that wonderful introduction to Bayesian statistics. It was really good. So what I want to do today, well, as always, these are the packages that I'm going to be using, and then you can follow along by downloading the Cordo document. So what I wanted to do today is kind of provide a gentle introduction to Bayesian data analysis. I want to keep this really high level and try not to use a lot of mathematical jargon, and I don't want to put a lot of formulas and scare everyone away. So today is going to be kind of a very gentle introduction to Bayesian data analysis and concepts important for Bayesian data analysis. And then I wanted to walk through how we can conduct, interpret, and report a very simple Bayesian model using the BRMS package. So if you're doing Bayesian statistics in R, you want to be using the BRMS package. It makes doing Bayesian analysis very, very simple. And we like things that make our life a lot simpler and easier. So when I was constructing this class, I knew that I wanted to include a week on Bayesian statistics. Right? And the reason why I wanted to do this is because over the last couple decades, we've seen a rise or growth in Bayesian statistics. And there's a couple of reasons for that. The first reason is that there's been lots of technological advances in computing. So our computers have just gotten better, they've gotten faster, and they allow us to fit very complex models. And related to that is these things called Markov chain Monte Carlo methods. And these make sampling from really complex distributions very efficient and very easy. I don't think if we had Markov chain Monte Carlo methods, we'd be able to fit Bayesian data analysis as well as we can now. And related to that, there's a whole host of packages that just make our life a lot easier. So with a couple lines of code, we can fit really complex Bayesian analyses. So in R, we have the BRMS package, and then there's also like GLM stan in R. And then also in Python, there's lots of good packages to fit Bayesian models. So PyMC, and then there's like PyStan, right, that uses a stan language. Ham, you could probably attest to this, maybe Alex too, if you've used that. Fitting Bayesian models are pretty easy using those packages, right? For the most part, for the most part. So back in the heyday, you would have to basically be a proficient programmer to model these Bayesian models, and now that's not the case. We could just throw our model into these functions, and we can run some Bayesian analyses. So that's one reason why I think that there's been a growth or rise in Bayesian statistics and the use of it. The second reason has to do with the replication crisis. So hopefully all of us know that science, psychology is in a crisis of confidence, right? So things that we thought were true have turned out to be not the case, right? And one of the reasons for this replication crisis, or one reason that's been cited, are p-values and null hypothesis significance testing. So there's been a misapplication and a misuse and a misunderstanding or misinterpretation of p-values and null hypothesis significance testing. So frequentist statistics in general. So things like optional stopping. So when we observe data coming in and we decide to stop once p is 0.05, right? That's done quite frequently. Hopefully we're not doing that anymore. You shouldn't do that. You shouldn't do that. And then there's things like p-hacking, right? So p-hacking is a whole bunch of different manipulations that people do to make that p-value less than 0.05. So throwing out data, rerunning different analyses, removing outliers, stuff like that, to make our p-value less than 0.05. So a solution to this problem is to just replace frequentist statistics with Bayesian statistics. And this is going to be this panacea that's going to solve all of our problems. I don't necessarily know if that's the case. I think that there's definitely still problems, but people have migrated from frequentist statistics to Bayesian statistics. So people are using Bayesian statistics more and more. So how many of you have read a paper recently that have used Bayesian statistics in some form? So reported a Bayes factor or a kind of full, complete Bayesian analysis? Yeah. So Nicole, no one else? Yeah, so I mean, it's becoming more prevalent in papers for sure. So this is why I wanted to talk a little bit about Bayesian statistics. And again, I have 1 week to talk about Bayesian statistics. There's whole courses on Bayesian statistics. So I don't expect, you guys to be, experts in Bayesian statistics after this one class session, but hopefully it piques your interest and you want to explore it more. And I'm hopefully going to give you the tools to be able to do that today. So if we were to Google Bayesian, or we were to search X or Twitter or my Twitter feed, what we would see is a lot of discussion, mostly centered on philosophical issues related to Bayes. So you'd see discussion on subjective versus objective probabilities, right? With subjective probabilities being associated with Bayesians and objective probabilities being associated with frequentists. You'd see squabbling between frequentists and Bayesians. Usually this is just why I'm better than you are. So Bayesians think that they're better than frequentists and frequentists think that they're better than Bayesians. So you'll see a lot of that discourse. You'll also see discussion on p-values versus subjective probabilities like Bayes factors. And the purpose of this lecture is not to go into those philosophical issues. If you're interested in those philosophical issues, I assigned an article for this week by Zoltan that goes into these issues, and I think it's a nice introductory chapter. So if you're interested in that stuff, please read that chapter. What I want to focus on today is Bayesian statistics as a tool. So the purpose of this class is to give you guys tools that you can put in your toolbox that you can use, when issues or problems arise. So you'll have that tool, and if you choose to use Bayesian data analysis, you'll have some tools to perform those Bayesian models or that Bayesian inference if you'd like to. I will say that throughout my years, I think I'm slowly becoming more Bayesian, in my methods, but I still see the benefits of frequentist statistics. And in a lot of my papers, I use both frequentist and Bayesian methods. I think that there's positives to both. So this particular lecture is not me saying like Bayesian statistics is the best and you should always use Bayesian statistics. I don't think that's the case. So let's talk a little bit about Bayesian data analysis. So what is Bayesian data analysis? So in a nutshell, we use Bayesian data analysis to quantify uncertainty using probabilistic statements. And within a Bayesian framework, we do this for all parts of a model, right? And we use that evidence to update our beliefs accordingly. Bayesian data analysis is a very flexible extension of maximum likelihood, which we've covered in this class before, right? So we know what maximum likelihood is, we know what likelihood is. Does someone want to remind us what maximum likelihood is? So if you're paying attention to Ham and Alex's presentation, what is maximum likelihood? What's the definition of it? And Ham and Alex can't answer. So. Anyone? Ham, do you just want to? So what's maximum likelihood?
Yeah, just to find the quantity that maximizes p data given the hypothesis.
Yeah.
Or each value of the hypothesis.
Yep. So like in a frequentist test, right, we're finding that best parameter that fits the data, right? And a core concept of Bayesian statistics is likelihood. We're just going to extend that here. What is Bayesian data analysis? It's something that can be computationally intensive. So in this class, we're used to fitting models and getting instantaneous results, right? Within milliseconds, we have our results. In a Bayesian framework, when we're fitting Bayesian models, it could take seconds, it could take hours, it could take days, or it could take weeks, depending on how complex your model is. I have run models that have taken several days before, so it all varies, but most of the time it takes a little while. It can be intensive. And also I want to emphasize too that Bayesian data analysis is hard. I think conceptually and also mathematically, it's a little harder to get into than the frequentist side of things, but that's okay. I mean, I'm still learning about Bayesian data analysis. It's something that interests me, but it's not something that I would consider myself an expert in by any means. And I'm still taking deep dives into various Bayesian concepts, but it is hard. So as I stated, Bayesian data analysis basically is a way for us to quantify unknowns, right? So what do we need in order to do this? So we need three things to do this. We need some prior information. So what's the state of the world before data is even collected? So this is why we associate Bayesianism with subjectivity, because we have this prior. So we assign a particular prior before data is collected, what we think the state of the world is before data is collected. We need some data, so we need to collect some data. And then we need a generative model. So what is a generative model? So a generative model requires fixed input. So these are parameters going into this black box here, our generative model here. And based off of this fixed input, we can generate likely values from it. And an example of a generative model is a probability distribution, like the standard normal distribution. So the standard normal distribution has two parameters, right? Mu and sigma. Mu is equal to 0, and standard deviation, or sigma, is equal to 1. Based off of this distribution, we can generate likely values. And we can perform things like Monte Carlo simulation, where we could do this thousands and thousands and thousands of times, and then we kind of build up a sampling distribution, right? And this is classic statistical inference, right? We build up our sampling distribution and we determine how unlikely our data is given that sampling distribution. That's statistical inference in a nutshell. Bayesian inference, Bayesian statistics kind of turns that on its head. So what we're doing here in Bayesian inference is we assume that the data is fixed, right? And we perform Bayesian inference to see the probability of various parameters given the data. And what's important to note here in that Bayesian statistics, the parameters are random variables that have distributions associated with them, right? We're not talking about one mu or one sigma. We're talking about a distribution or a vector of likely values given the data. And essentially what we're interested in Bayesian data analysis is the posterior, which is the probability here. Instead of saying parameter, I'm just going to say theta, given the data. This is our posterior. And I think Ham and Alex did a really great job kind of going over Bayes' rule and all the different components here. So I'm not going to spend time talking about the components of Bayes' rule. But what I wanted to do is kind of show an alternative kind of depiction of Bayes' rule in terms of distributions, right? So the parameter values are essentially distributions of likely values. So we can see here that the posterior, we have this distribution here of likely parameter values is a function of both the prior, and this prior has likely values associated with it, times the likelihood, which has associated values with it, divided by the evidence here. And we can see that the evidence, or the marginal likelihood, is just the integration or the sum across the entire parameter space here. And most times we can't directly compute this marginal likelihood. We can in very simple cases. So if we're working with one parameter like theta, we can easily compute this. It's relatively simple to do so. But in complex models, we have hundreds of parameters, or we might even have thousands of parameters, and this becomes intractable where it's hard. But the good thing is that this is usually a constant, right? A single number. So oftentimes what we do is we just sweep this under the rug and we rewrite Bayes' rule as a proportional formula. So we replace the equal sign with just a proportional symbol here, right? So the posterior is proportional to the prior times our likelihood, right? So this makes our life a lot simpler when we rearrange the Bayes formula here. All right. So are there any questions so far? So Bayesian data analysis requires a prior, it requires some data, and then based off of these two things, we can update our beliefs. So what I have here is kind of this Bayesian belief updating cycle. And what I wanted to do is go through each of these steps. So I want to go over prior knowledge and talk about the prior distribution and prior model odds. I want to talk about prediction and the prior predictive distribution. So using our prior, what are the likely values associated with that prior? I want to talk about data and prediction error, so things like marginal likelihood and Bayes factors. And then I want to talk about updating our knowledge. So the posterior distribution, the credible interval, and posterior model odds. So these are important concepts in Bayesian data analysis that I think that we should know a little bit about. So what I wanted to do here is work with a very simple example. So let's say we're interested in the percentage of dog people in the US. So state of facts, people could be classified as dog people or cat people. Who in here are cat people? Who in here are dog people? Okay, see, so you're either a cat person or a dog person. So our data is 0 is a cat person and 1 is a dog person, and we're going to be looking at just one parameter. This is theta, and this is the proportion of dog people. The first step in Bayesian data analysis is establishing a prior distribution. So the prior distribution represents our beliefs about a parameter before the data is collected. And that's key, before the data is collected. What's the state of the world before I see any data? And what I have depicted here are 2 possible priors for our particular example. So in green here, we'll just call this model 1, is what's called a spike prior. And this is a very extreme prior. What this prior states is that we are 100% certain that 50% of individuals will be dog people. There's no other value of theta that's likely. It's going to be 50%. So this is model 1. Model 2 here has some uncertainty associated with it. The distribution is a little wider. In this particular distribution, the most likely value is probably 0.5, but it can also be 0.25, it can also be 0.75, right? So it assigns probability to some other values here. So it's a wider prior. And there's a number of other priors that we could use here. So I just went over a spike prior that's kind of centered at 0.5. We could also use a prior where 0.6, 0.7, and 0.8 are likely values, with 0.7 being more likely. We could fit what's called a uniform prior, which assigns equal probability to all of the parameter values. And we could also use beta distribution. So beta distributions are really good for proportions. And next week, we're going to talk about beta regression. But we can fit a beta prior here. So we talked about this. This is our model 2 here, where it's centered over 0.5, but there's also other possible likely values. We could fit a beta model where smaller values of theta are more likely. But we could also fit a beta model where larger values are more likely here, right? So there's a whole host of different priors that we could use. And I think that this is what makes Bayesian data analysis so difficult, at least for me. This is probably one of the most difficult things for me about Bayesian data analysis is declaring these priors, right? What prior do I use? Is the prior that I used, is that good? Is it bad? It's difficult. And one thing that makes it really difficult is that you have to establish prior information for all the parameters in your model. So if you're fitting a normal distribution with a mu and sigma, we need to have parameters or priors for those parameters. So it can be really hard. And people argue all the time about priors, and priors can differ in 2 ways. They differ in how informative they are and also how proper they are. And this creates 3 camps. There's subjective Bayesians, there's objective Bayesians, and then there's most Bayesians, which I fall under. So subjective Bayesians usually use what are called informative priors. So these priors rely on theoretical expectations or theoretical considerations and experience. And these priors are very specific. So for example, I might state that the true correlation is negative 0.5. Right? I know the data really well, and I know that before data is collected, the correlation should be about 0.5. That would be an informative prior. Objective Bayesians use what are called non-informative priors. And an example of a non-informative prior would be this uniform distribution that I showed, where all values of theta are equally likely, right? So this doesn't really give you any information. All of them could be likely. So for example, I might say that the true correlation is between -1 and +1, which is pretty wide, and any of those values could be the correct value. And then most Bayesians fall under this weakly informative prior, and these priors are constructed to not bias the estimate, right? Or bias the estimate the least. So here what we do is fit distributions that are fairly wide. So we might fit a normal distribution with a mean of 0 and a standard deviation of 100, right? Where we're not really sure what the effect is. It could be small, it could be large. And this is where I fall. I try to apply weakly informative priors to my data. I don't really know a lot about priors or what the prior should be, and I think that's the case for a lot of us. So weakly informative priors are pretty good, and they're actually pretty important for calculating things like Bayes factors as well. We can also state our priors in terms of how strong they are. So a subjective Bayesian, one that implies informative priors, might state their belief very strongly. So they might state that the normal distribution there's a correlation of 0.3 with the standard deviation of 0.06. I think that's what Ham did in your data, right? You probably had pretty strong priors on your.
I try to make it as weak as possible, but because
they're pretty informed though.
Infinity to positive infinity, you cannot do a literal uniform.
Yeah.
Right, the density will be 0 everywhere.
But they were pretty informed, it looked like, for the most part.
I did the normal distribution prior, constraint on 0. So like you don't want to deviate from 0 unnecessarily.
Yeah.
Basically.
Yep.
Yeah, I guess that counts as deeply informed.
Yeah, but you also probably put a small standard deviation on there too, and the upper bounds maybe.
Yeah, I want to be as small as possible. I think what I did is like to go as small as possible and then it's giving me divergence.
Yeah.
I'm just gonna turn it back on.
Yep.
No divergence. Yeah, done.
Yep. So you might state your belief strongly. So Ham probably didn't state his belief that strongly, but it might be an informative prior. The downfall to that is that if you state something very strongly, then that's going to have greater influence over your posterior distribution. But as Alex and Ham already went over, if you have lots and lots and lots of data, the prior doesn't really matter that much. But it does matter if you have small amount of data, right? If you have a small sample size, then the choice of your prior actually matters a lot. You might state your belief or your prior very weakly. So if you are stating something or if you're applying a non-informative prior distribution, such as like uniform distribution, or that you state that the value is between -1 and 1, that would be stating your belief weakly. And the pitfall of this is that you can overestimate the densities of your posterior to your prior. What that means is that the posterior distribution is going to swamp the prior distribution, right? So the prior does not really matter. And that could be a good thing, but that could also be a bad thing. I don't think of necessarily as a bad thing because the data is going to tell you what it is anyways. So I don't think that that's a bad thing, but it could be a bad thing depending on what your question is. All right, so let's go back to the Bayesian belief updating stages here. Are there any questions about priors? Yes.
So I think in case of like a lot of what we're interested in, we can apply the same prior to all conditions. So you can think of priors as yes, it's biasing towards a particular value, but it's applying the same bias to all the conditions. So if you're interested in like difference across conditions, then that's still justified. Yeah. Although the exact size may be washed out a little bit because of the bias. Yeah. So in that case, we wouldn't worry too much about it's biasing your results.
Yeah. I mean, my approach is to apply weakly informative priors or default priors, but usually weakly informative priors, I'll apply to them to bias the estimates the least. That's my approach at least. So we have these two models, right? We have the green model and we have the blue model, and we could replace these models with people if we wanted to. But if a third person comes along and is trying to decide between model 1 and model 2, a rational person would apply 50-50 odds to these prior models, right? I don't know which one is right. So it could be model 1, could be model 2. So specifying these prior distributions allow us to calculate things like prior odds. With prior distributions, what we can do is we can make predictions about the plausibility of the data. So we can take our prior distribution and generate likely values. So in our case, let's say that we sample 5 people and we observe 0 dog people, 1 dog person, 2 dog persons, 3 dog persons, etc. We can actually make estimates for the probability of observing those values. And that's what I'm highlighting here. This is this prior predictive distribution of likely values. So what we can see here is that values 2 and 3 are more likely under that spike prior, right? So there's higher probability for the green model compared to the blue model. The blue model is a lot wider and there's more uncertainty associated with it. So it actually assigns more probability to zeros and ones, or zeros and 5s. But also 1 seems to be more probable under the blue model, and also values of 4 seem to be more probable around the blue model, right? Because there's a lot more uncertainty associated with those values here. So specifying a prior prediction distribution allows us to kind of estimate what the values could be. So now let's go ahead and just collect some hypothetical data here. So let's say I just sampled 5 people, and 3 of those people are dog people, and then 2 of those are cat people. What we can do now that we have the data is we can calculate what's called a marginal likelihood, right? This is the probability of the data given some model. And this is very similar to the prior predictive distribution, right? where we use the prior predictive distribution to calculate the likely values of plausible data points. Here, we're evaluating this prior predictive distribution, so the spike prior or the wider prior, at the observed data, because we've collected that data here. So what we can do here is we could take our prior distribution here and evaluate it at the observed data and get a probability estimate here. So given this parameter or this prior of 0.5, right, what's the likelihood of x equals 3? We could get a probability, we could use the binomial function, and it'll be like 0.31. We can do that for this prior as well and get a probability estimate for x equals 3, and then we can do that for this prior distribution as well and get a probability statement here, right? So this is a lot lower, right? Because this particular prior distribution stated that lower values of theta are more probable, whereas we observed a higher value of theta, right? So x equals 3 is lower in this sense, given the data. So which model is the right model given the data, right? We have two models, right? Model 1, model 2. We could have model 1, 2, 3, 4, 5. Which one's better? So what we can do is we can calculate what's called a Bayes factor, and this will tell us which model is more likely. And Bayes factors is an important concept in Bayesian statistics. So frequentists have p-values, Bayesians have Bayes factors. And if you're a hardcore Bayesian, I don't know if you're using Bayes factors, but me as a psychologist, I use Bayes factors. I like Bayes factors. And Bayes factors is usually abbreviated as BF. And what Bayes factors tell us is how much more likely the observed data is under one model compared to another model. And what's really cool about this is that we can interpret this as degrees of evidence. So we can get evidence for one model versus the other model. And to calculate a Bayes factor, we're basically just taking the ratio of marginal likelihoods, so the probability of the data given model 1 divided by the probability of data given model 2. We can replace these models with hypotheses if we want to, but we're working with models here. And taking the ratio of these two things gives us our Bayes factor. And that's what I'm highlighting here. For our particular model here, we can calculate a Bayes factor, and we usually use subscripts, and we usually use the comparison of the model. So if we have a subscript of 1, 2, that means that this is the Bayes factor for model 1 versus 2. And we see that the Bayes factor is 1.46. So what this means is that model 1 is 1.46 times more likely than model 2. So if our Bayes factor 1, 2 is greater than 1, that means more evidence for model 1. If it's less than 1, there's more evidence for model 2. We could also take the reciprocal of this, right, and get the BF for model 2 versus 1 if you wanted to do it. So let's make this a little bit more concrete, and let's calculate Bayes factors for our models. So for model 1, we're using that spike prior here, right, centered at 0.5. So the probability that x equals 3 given model 1 is about 0.31 if we calculate it. We can also calculate the marginal likelihood for model 2. So what's the probability of x equals 3 given model 2? And that is 0.16. And what we could do is we could just divide these two things and we could get a Bayes factor. And the Bayes factor subscript 1, 2 is equal to 1.896. So how we interpret this is that model 1 is 1.896 times more likely than model 2. So what the heck does 1.896 even mean? How do we interpret this? Is this good? Is this bad? Well, luckily there's heuristics that we can use. If you read the Bayes factor paper today, they provide several examples of heuristics. This is Jeffrey's heuristics that a lot of people use. And this basically allows us to apply some label to our Bayes factor value, right? So we can see here that a Bayes factor of 1 means that there's no evidence. A Bayes factor of 1 to 3 means that there's anecdotal evidence. 3 to 10 is moderate evidence. 10 to 30 is strong evidence, right? Hardcore Bayesians would probably hate me for saying this, but that's okay. But I find Bayes factors extremely useful, right? So we can use these Bayes factors to tell us how convincing our evidence is. So in our case, we got a Bayes factor of 1.896. So that relates to anecdotal evidence for model 1 here, right? So not that convincing. It is greater than 1, but it's not really that convincing. If we wanted to publish in psychology, we couldn't publish this finding because if you want to publish in psychology, and I don't know how it is in other journals, they usually want you to show moderate to strong evidence for your Bayes factors. So greater than 3, yeah.
I'm just wondering why
Some people use log odds to make it simpler to infer or interpret. So you will see that sometimes where you just have the log of the Bayes factor to make interpretation easier. So they will use that sometimes. All right, so now that we have some data, now we can actually update our knowledge. So we can do this by computing what's called a posterior distribution, which is a distribution of parameter values that represents the beliefs about a parameter after we've collected the data. And this is highlighted here. So if you remember, this green spike prior is model 1, and then this dotted blue line here is the prior for model 2. And we have this solid blue line here. And this is our posterior after seeing the data in relation to model 2, right? So hopefully we can see here that that posterior distribution has shifted, right? We've observed the data, x equals 3, and now we see that the actual theta value is centered on 0.6, what we observed with the data. So our beliefs have been updated given the data. And that's what a posterior distribution tells us or shows us. So there's something missing here. This green spike prior doesn't have a prior distribution. This green prior doesn't have a posterior distribution. Why would that be? So it's missing from this graph. Anybody want to take a guess why there's no posterior distribution there? So we've stated so strongly that there's a 100% probability that the value is 0.5 that there's nothing to update, right? So for example, let's say that you're 100% certain Santa Claus doesn't exist. So you wake up on Christmas morning and you see presents under the tree. Does that change your beliefs about Santa Claus? No. So there's really nothing for us to update. We said with certainty, there's a 100% probability that there's gonna be 0.5 dog people. We collect the data, it's 0.6. We said at 100% certainty it's gonna be 0.5, so there's nothing to update. So this is an example of using different priors and how the posterior distribution looks in comparison to those priors. So we can just see how the evidence has been updated depending on your prior here. So with our posterior distribution, we can calculate what are called credible intervals. And this gives us a way to express uncertainty in estimating our parameter values. So it's basically a range in which we believe the true value lies with a certain probability, right? So we can say with a probability of 95% that the parameter lies within this interval right here. What is this conceptually related to that we use quite frequently? Yeah, confidence intervals. Does anyone want to take a shot at defining what a confidence interval is? So a lot of people like to interpret confidence intervals in the frequentist sense as credible intervals, but they are not. So we need to be very careful in how we define confidence intervals. So with confidence intervals, we're taking hypothetical samples, right? So we can think of an infinite number of samples, and 95% of the time, the parameter is going to lie within that interval, right? So what's important is that we're talking about hypothetical samples from a population. Here, we don't need to do that. This is what I think one of the most powerful things about Bayesian statistics are these things like credible intervals, because we can assign probabilistic statements to these things. So I can say with 95% certainty that our parameter value is going to lie within this interval. We can't do that with confidence intervals, although you will see a lot of people define confidence intervals in this way. They are not the same thing. With confidence intervals, or excuse me, with credible intervals, we can assign probabilistic statements to these intervals, which I think is really powerful. All right, so how much do we update our beliefs by? So we can update our beliefs by calculating what are called the posterior model odds. And the posterior model odds is basically just prior odds, so what we believe before we see the data, times our Bayes factor is what the evidence is after collecting data, right? So we just take those two things and multiply them, and we have our posterior model odds here. And because our our prior odds was just 1, right? 0.5 divided by 0.5. Basically, our posterior model odds is just the Bayes factor of 1.46, right? So there is some evidence for model 1, but it's possible that we don't update our beliefs that much, or we're just like, I still really don't know which model is right, model 1 or model 2, if we're going to use those heuristics here. All right, so that was a kind of a quick, gentle introduction to Bayesian concepts. So now what I want to do is I want to walk through how we can conduct, interpret, and report a very simple Bayesian regression using the BRMS package. So with the data set, we're going to try to answer this question. Does synchronous attendance or mode of attendance and average viewing of recorded lectures matter in a hybrid statistics course? So we have data, a very small data set with 33 students from a statistics course in fall of 2020. In that data set, we have 3 columns. We have a grade column, which is the final course grade. The min is 30 and the max is 97. Sync is a column, and that's just the mode of attendance. So 0 if they attended asynchronously, or 1 if they attended synchronously. And then lastly, we have average view, which is just the average viewing time for the recorded lectures, and that's in minutes. So these are the 3 variables that we're going to look at. So let's go ahead and just load in our data. And because these are so intense, we have to I can't actually run this in the Cordo document itself, or it just takes a long time to actually compile the document. So what we're going to do is we're just going to actually go to RStudio and run it in RStudio. So let's go ahead and load in our data set. And I'm going to go back and forth. And then these are some important packages that we'll need to run our Bayesian regression. So just taking a look at the scatter plot for our average view variable here, with average viewing time on the x-axis and then grade on the y-axis, what we can see is that as you watch more recorded lectures, you tend to do better, you have a higher grade. That makes sense. Looking at our sync variable here, what we see is that those that attend synchronously seem to do better or have higher grades than asynchronous students. But hopefully we can see that there's lots of variability in the asynchronous level, and there's not that many data points in the synchronous level here. So let's just fit a very simple regression to start off. That's something that we know, and see what it tells us. So this is the regression model output. And what we can see here is that the average viewing variable is statistically significant, right? So P is less than 0.01, and the coefficient is 0.46. So as viewing time increases, there's a 0.46 increase in the grade that you receive. The synchronous variable, however, is not statistically significant. Now let's go ahead and fit a Bayesian regression model. And we're going to fit this Bayesian regression using the BRMS package. And this stands for Bayesian Regression Models in STAN. And this is developed by Paul Bruckner, who's in Germany. So he developed a really great package to perform these Bayesian models. And this particular function that we're going to use, the BRM function, is very versatile and flexible, and it can fit a whole host of models just simply by changing this family parameter here. So all the models that we've talked about this semester, we can fit with just the BRM function. We can fit zero inflated models, we can fit logistic models, we can fit multinomial models, we can fit ordinal models, all using this syntax here. So let's just go ahead and fit a regular linear regression here, where we're going to look at average viewing and then the synchronous variable, predicting grade. This is our data. The family we're going to use is a Gaussian distribution. So if we're going to do normal statistics, we usually use a Gaussian family. We change that up if we're going to do some type of generalized linear model. There's a whole host of different families that you can use. We're going to set our prior to null. So how many chains do you run? This is related to the Markov chain Monte Carlo sampling that's done to compute the posterior. And by default, we want to set this to 4. So we want to run these samples on 4 chains. Core relates to how many computer cores on your computer you want to use. This is to make the sampling more efficient and faster on your computer. We usually set this to 4. So each of those chains is going to run on each of those cores. Warm-up has to do with the Markov chain Monte Carlo sampling. And then we have iteration, which is 5,000, which is the number of samples we're going to do. These warm-up samples are actually just to get the Markov chain Monte Carlo sampling warmed up. and we don't include those in the final analysis. We kind of throw those out. So out of these 5,000 iterations we're going to run, 2,000 of those are going to be thrown out as burn-in samples. So let's go ahead and run this real quick in R, and we'll kind of see how long it takes to run. Just gonna do that. So as we can see, it's not very fast. So the wrapper, so BRM is a wrapper to the STAN language or the STAN coding language. And this makes, using this language or the BRMS package, it makes using the STAN language very simple and very easy. You could write your own STAN programs if you'd like, if you are, computer savvy, but we don't need to do that because of the BRMS package. All right, so we've run our models here. We can see that there's 4 chains, right? And each chain is going to run 5,000 iterations. So let's go ahead and look at our summary report here. So if we look at the summary here on the top, we have some meta information, right? So we use the Gaussian family here, and then we use the identity link. This is just fitting mu and sigma from our normal distribution. We have our formula here. We have 33 observations. Draws refers to the number of draws that are done for the MC sampling here. So we have 4 chains, each with 5,000 iterations, and then we have a warm-up of 2,000. Thin refers to how many of the Monte Carlo or the Markov chain Monte Carlo samples we want to take. Here we're just taking all of them. If we set it to 1, if we set thin to 5, it would take every 5th sample. And then now we have these population level effects here. And these are our posterior estimates. And these can be interpreted in the same way that we interpret our linear regression output. So we have our intercept value here, which is the value of y when x equals 0. We have average viewing time here. So for a 1 unit increase in average viewing time, how much does the dB change? And then the synchronous variable. If we contrast coded this, this would be the difference for that particular estimate here. And we also have other information here, like the estimated error, which is our standard error. And we also have the CIs, which are credible intervals. So we have our 95% credible intervals. And we also have things like R hat and ESS, and I'll explain what those are in a bit. And then we also have our posterior distribution for our other parameters like sigma, and that's what's contained here. So this is kind of the basic Bayesian output. So how are the posterior estimates computed? So we use this kind of really cool method called Markov chain Monte Carlo sampling, or MCMC. So given our priors and our data, we use Monte Carlo sampling to build what are called Markov chains. And we call this MCMC. And we run these chains across 4 chains in our model with equal number of iterations. And these chains contain our samples from the posterior distribution. And what I wanted to do was I kind of wanted to break apart MCMC, and I wanted to talk about the first MC, which is Markov chains. And Markov chains are a really cool, interesting way to explore kind of an unknown parameter space. And what Markov chains are essentially is a chain of discrete events that move forward in time, where the probability of each event is conditional on the last event. And these Markov chains are memoryless, meaning that future events are wholly determined by the current state, right? No other information is included in this movement across the parameter space. So I have an example of a very simple 2-state model here, right? E and A. So if we're at E and we want to move to A, maybe we calculate this transition probability and it's 0.7. If we want to stay in the current state, it's about 0.3. So I might decide to move to A. And then when I'm at A, I might decide to move to E. So I calculate the probability for that, but I might stay at this current location, which is 0.6. And this is a nice little animation of kind of how you move through this parameter space here. And one issue that can arise here is that you might stay in the same loop and not explore the parameter space. These Markov chains are used quite frequently in machine learning and also in computer science. So Alex is using a variant of Markov chains in some of the work that he is planning to do, right? So you're using hidden Markov chains. I don't know if you want to add anything into this or if I provided an accurate representation of them. But in a nutshell, this is kind of what it's doing. It's kind of just exploring the parameter space. The second part of MCMC is Monte Carlo simulation. So we've talked about Monte Carlo simulation before, right? So we have this known distribution and we sample from that distribution. And we usually take an average of those samples. And that's what this code is highlighting here, where I'm just doing 100 simulations with a sample size of 100 with a mean of 0 and a standard deviation of 1. And then what I'm doing is I'm using this rnom function, and I'm basically performing these Monte Carlo simulations, taking 100 samples, getting the mean, and then doing it again and again and again and again. For some reason, I can't run this, but that's okay. So what does this actually look like in action? So there's this really great Shiny app that demonstrates what this actually looks like. So there's a whole bunch of different MC algorithms that we can use here. I think under the hood, BRMS is using Hamiltonian Markov chains, which is beyond my skill set. It originates in physics. So maybe Renata can explain Hamiltonian physics to us, but that's the essential kind of theory underlying this thing. So we can see in a standard normal distribution how we're exploring this parameter space here, right? We're starting at a particular point, we're taking a whole bunch of samples, taking some average or mode of that sample, and then building up this distribution here, as we can see here. And we do this for all the parameters in our model here. Which I think is a nice kind of cool demonstration of what's going on here. Yeah. Yeah. That's like the Gibbs sampling, right? Fanning out.
That's all. You're just considering different things, and then your acceptance function considers a bunch of options.
Yeah.
So it's just more efficient.
More efficient, yeah. And I think that's why BRMS uses Hamiltonian versus the other, because it seems to be better at sampling the space. So that's MCMC in action. So as I said before, we could get in this kind of circular pattern where it just goes in the same loop and doesn't, sample the parameter space entirely. So what we can do is we can look at some diagnostics to help us determine if the MCMC sampling kind of performed properly and it converged. One visual way we can diagnose this is with trace plots. And this is an example of a trace plot where on the x-axis you have the number of iterations that you completed, and then on the y-axis you have the actual parameter space. And so this is basically how the parameter space was interpreted at each iteration. And essentially what we want to see is something that looks like a fuzzy caterpillar. This means that the sampling was efficient and that it converged successfully. So we want to see this fuzzy caterpillar, and a central characteristic is called stationary, where every chain is basically sampling from the same sample space, right? So the same mode and same mean. Right? So all of these iterations are exploring the same parameter space. And that's what we want to see here. This is an example of a bad trace plot. So we can see that we don't have stationary, right? So we don't see that all of the samples are estimating or exploring the same sample space. We see that there's some divergence here, right, where each chain is kind of exploring different areas. This is something that we don't want to see in our trace plots. We can also use numeric methods to help us diagnose this. So as I said before, when we looked at the summary output, there is a column called R hat, and this is just a measure of the consistency of our Markov chains, and we want our R hat to be very close to 1. If it's larger than 1.01, then we might have some issues with convergence and we might need to make some changes. So we can think of this R hat value as just a ratio of variance like an F-test, where we're looking at the ratio between variance, so the between chain variance to the within chain variance. In this particular case, our between chain variance would be very large, and that's not something that we want. We want the chains to have very small between chain variance, right? We want them to be overlaid on top of one another. Another diagnostic that we should look at to diagnose the efficiency of our MC sampling is ESS, which is just the effective sample size. And the effective sample size is just the number of independent pieces in our Markov chain Monte Carlo simulations. So MC samples are autocorrelated, right? So if you remember how we're searching the parameter space where future events depend on the current state, they're autocorrelated. So there's less information going into the estimation. So we want to make sure that ESS is very large. So the rule of thumb is that ESS should be greater than 1,000. If it's not greater than 1,000, then we probably want to up our iterations and run more iterations for each chain if ESS is not big or large. All right, so now I want to talk about priors. So we can assess the priors that are used in our model by using the prior summary function. So if we run our prior summary function, and remember, we use default priors. We did not set any priors. What we'll see is that our priors that are used by default are flat. These are basically non-informative priors. So remember that kind of horizontal straight line? That would be a flat prior that we're using here. And we're assigning a flat prior to all of our B coefficients here. So our average viewing and our synchronous coefficient here. And then it also assigns a little bit more informative priors on the intercept and sigma, and it uses information from our model to do this, but they're still kind of weak or non-informative here. And as I said before, non-informative priors will give you essentially the same results as a frequentist analysis. So I had you guys do this in the ordinal lab, where you ran the BRM function for the ordinal data, and the results were essentially the same, right? There was no differences. But we shouldn't use non-informative priors. We should use weakly informative priors. And this is an example of one weakly informative prior that we can use that I've used. It's basically just a normal distribution centered at 0 with the standard deviation of 10, right? So we're not making any assumptions that the effect is not 0 here because it's centered at 0, but we have a pretty wide distribution, right? So it could be, it could be larger values, but it's probably most likely smaller values, but it's not ruling out some of the larger values for our estimate parameter. Another type of weakly informative prior that's widely used is a Cauchy prior with a mean of 0 and a width of 0.707. If you use JASP and done Bayesian analysis in the JASP program or some of the other programs in R, they most likely use this Cauchy prior as a weakly informative prior. By default, this is used. And this particular distribution is very similar to a normal distribution, but it has super wide or fat tails. And within this particular distribution, when we set the mean to 0 and the width to 0.707, that means that 50% of the probability is going to lie between these two values here, right? So this is used by default in a lot of programs or packages that you use. So we can set our prior information by using the prior argument from the BRMS package here. And I've highlighted here the setting of 3 different priors. So a Cauchy prior and a normal prior, and then a normal prior with a very small standard deviation here. And what we can do with this is we can actually look at the prior distribution to see if it makes sensible predictions. So we can just fit a Bayesian model with just the prior information. And we can use this to see if sensible predictions are being made. Is this producing negative values when our actual DV has no negative values? Those are the things that we want to look at. And we can do that by running a Bayesian model with BRM and then setting the sample prior argument to only. So this is only going to sample from the prior that we specify. The prior argument is not null anymore. It's actually prior to, so with a normal of mean 0 and standard deviation of 10. And we can run this model, and then we can do the PP check to look at our model and how it compares to our prior predictive distribution and the samples that it makes here. And what can we determine from this? I know it's kind of hard to see, but this is a pretty horrible prior. We can see this big, huge mode here, or mean here, compared to what the actual model is predicting here, right? So this would probably be a very bad prior. Right? It doesn't match with our actual data or what we think the data should look like. And we should probably only do these things if we're using informative priors. But this is one way to check to see if we're making sensible predictions. In this case, we're not. So now I want to talk about describing the posterior. And does everyone have about maybe 10 more minutes? Or do people have to leave at 11:20?
We have to go, yeah.
You guys have to go at 11:20? Okay. So what I'll do is I will hold off. And what I'll do is I'll probably post a video basically describing the rest of this lecture because I don't want to keep you guys here longer than you need to. So this is where I'll stop for today, and then I will post a video highlighting the rest of the lecture for you guys.